Start recording. Yes, we are recording. And I hope everybody can hear me all right for a change. I got the news that we have brand new batteries bought for my mic. And in any case, we will change them during the break. So I hope no more snafus with batteries or for another reason. Okay, so today what I want to tell you about is the first part about the structure of graphs, directed graphs. And I will handle three things today. For starters, I want to define to you what it means that a graph is connected. And then I want to really say everything or almost everything about subsets of vertices being hereditary and saturated. These are absolutely pivotal concepts for Leavitt path algebras, for graph system algebras, and this is what we're going to cover today. Okay, so for starters, I need a definition of an unoriented, undirected path. Okay, so let E be a graph, as usual. An undirected finite path whenever we say a path, we usually mean a finite directed path. Since undirected paths are used very rarely, this is why they are decorated with an adjective, okay? Because it could be that a path means undirected path, and we must say directed path when we mean directed path, but it's the other way around due to the importance of one over the other. Okay, so such an undirected finite path in E is a finite sequence of edges satisfying at least one, satisfying at least one of the following equalities. So one, well, we might have a situation that at a given edge, I didn't know, is a finite sequence of edges, and here I write EI. Well, maybe I should write down E1, comma, up to En. So here we have EI plus 1. So you see, we have two arrows outgoing from the vertex in the opposite direction, okay? So I can just write it down as S of EI equals S of EI plus 1. So this is one possibility. Another possibility is that arrows go to the left and they meet in this middle vertex. So EI plus 1. And now what do I say? I say that the beginning of the edge EI is equal to the end of the edge EI plus 1. The third possibility is when they go in the opposite direction. And then, of course, we'll have that the end of EI is equal to the beginning of EI plus 1. And finally, they can both point into the middle vertex. And then we'll simply have that the end of EI is equal to the end of EI plus 1. And this must be satisfied for all I that belong to the set from 1 to n minus 1. Okay. So of course, yeah, I mean, when n is equal to 1, this doesn't make sense But when n is equal to 1, we just give an edge, and an edge is always both a directed and an undirected path. And if n is bigger than 1, at least 2, well, then we have to consider such possibilities, right? And when we range I from 1 to n minus 1, we have all possible meeting points of edges that form the path. So in other words, this is like a directed path, except that you can orient the edges in a directed path any way you want. Okay, and I needed just to define the concept of a connected path. Sure. At least one, because you see, this is just a generic situation, but you can imagine that you have loops. And for instance, if EI plus 1 is a loop, then it will satisfy 2 equalities. Yeah, yes. Yes, exactly, yes, of course. Yeah, but this is a good point. This is a very good point, how to make it logically clear. Yeah, this is a very good point. For every I, so maybe I should put the quantifier earlier. Yeah, let me put it here, right? Then maybe it's unambiguous. A finite sequence of edges satisfying for all I at least one of the following. So I choose an I, and for this given I, one of the following equalities must hold. At least one, not necessarily just one. If I have just loops, then all equalities will hold. Yeah, you can imagine this situation. This is my EI, and this is my EI plus 1. Then all 4 equalities will hold. If you want to speak, you should use a microphone so that other people can hear you.
I mean,
yeah, it's working. It's working. It's working. People can hear you.
Okay. So I mean, if one of the paths is one of the 8 is isolated with each other, so none of this satisfied.
Exactly.
So we could not have this way.
Exactly. This is exactly, but this is not the path. When I have a situation like this is not the path.
Okay.
Because I have a gap in between.
Yeah. Okay. So
that's the whole idea.
Piotr?
Yes.
Piotr?
Yes.
You can just define it to be the equivalence relation given by.
Sure.
Right. Then
I kind of mentioned it. You have a forgetful functor from oriented paths, usual paths, directed paths into the undirected paths. Yeah. Of course. Yeah, but this is all equivalent, and this is such a simple concept. I don't think we need to ponder around it much longer. This is just a hands-on situation, definition. You have 4 possibilities, and at least one of them must be satisfied for every I. Okay? So this is a definition of an undirected finite path. Well, now I can wonder what an infinite path is. Well, let me write it down. Although I don't think this is very useful. I just need a bigger piece of chalk because a small one gets in between my gloves and the board. So an undirected infinite path is an infinite sequence of edges I should draw this line, which I should now go beyond. Okay. So I have EI, I running the index at I, where I is either natural numbers or integers or minus natural numbers. And satisfying maybe like here, for all I in I, when I is equal to N or Z, and for all I not equal to 0, when I is equal to minus N. Sorry, this is a Blackboard I. Okay. So for all i's, it has to satisfy, again, one of the satisfying at least one of the above 4 equalities. And this awkward hiccup here that I have to take negative natural numbers separately is because of the way I wrote these equalities. It's I plus 1. So when my numbers end at 0, I don't have 1. 1 is not a negative natural number. So the biggest I can take is minus 1. If I do integers or natural numbers, yes, I can take all of them. And no matter how you phrase it, you have to do one case separately. Okay, so this is just a definition of undirected or unoriented. I don't say disoriented, it would sound very negative. Unoriented, undirected paths. Yeah, that can be defined in many different ways, but here we go. That's, I believe, one of the simplest ones. But why do I need it? There's just one reason at this moment, at least why I need it, because it has a bearing on graph algebras. I want to tell you what it means that the graph is connected. By the way, it's obviously, right? A directed graph is a quadruple. I have a set of vertices, a set of edges, the source map, and the target map. That's it. No. Yeah, sure.
You ask some example of which looks at the graph, in my opinion, but it's not a graph, not a direct graph or undirected graph.
Well, well, for instance, if you people also consider, and it's widely considered, unoriented, undirected graphs, and then simply you have edges which are not oriented. I mean, you don't have such a thing as a beginning and end, okay? And this would be an undirected graph. You have here an edge, here an edge, here an edge, but I don't draw arrows. I cannot say where the beginning is and where the end is. So this would be an unoriented graph. And it's often considered. Also, people often consider graphs such that there is between 2 different vertices. So here I have 1, 2, 3, 4 vertices. That between any 2 distinct vertices, you have only 1 edge. Sometimes it's also important. Yeah, that's what I know from.
So it's like a tree graph, like a loop graph. I mean,
well, I don't know. This is not a question whether you allow loops or not. I said about the 2 distinct edges, but well, maybe it's important to bear in mind that even though I draw it on the blackboard, this is not a subset of a plane. I mean, you don't have a braiding. You don't care whether some edge goes above or below. No, I mean, it's just the only thing that you know about your edges is where it begins and where it ends. That's it. Okay. And then you can give a meaning to directed paths. Yeah, which is very crucial. We are studying it for much of the semester. Okay. But this would be an example where we don't care about the orientation. And yes, indeed, people consider it. It's quite popular. I never looked into it, but there is some huge chunk of mathematics concerned with undirected graphs. Okay, so what does it mean that the graph is connected? So we say that a graph E is connected if for any pair of distinct vertices pair VW be not equal to W of vertices, there exists an undirected path, or an undirected finite path. Yeah. There exists an undirected finite path, so P1, E1 to En. Maybe I should write undirected. Exists undirected. Okay. Such that we have that the beginning of E1 equals to V or the end of E1 equals to V. I put it in parentheses because I have a conjunction of alternatives. So pure English is not enough. And I don't like these logical symbols. Yeah, V and W, yeah. Yeah. Or, and the beginning of En is equal to W, or the end of En equals to W. So in other words, to put it briefly in words, a graph is connected if for any two distinct vertices there is a finite undirected path joining them. Okay? And this was the only reason why I needed to define an undirected path. And later on, you will see that if you have a disconnected graph, then the Leavitt path algebra of such a graph or graph system algebra of such a graph will give you a direct summand of graph algebras related to each of the connected components. Okay, so this is a worthwhile definition because here this connectedness somehow survives all these Kunz-Krieger relations, and disconnected graph means kind of disconnected algebra in the sense that it decomposes into direct summands. Okay. Good. So that's all. No, sorry. There's actually an interesting theorem that we can prove. Well, actually, it's a proposition about connected graphs. Yep. So today, I like the structure because every of these boring elementary definitions is followed by an elementary but cute proposition. But before phrasing this proposition, I need one more definition. This is just terminology. But it's a very common terminology, so we better introduce it. A vertex V in a graph E is called a sink whenever it does not emit any edges. So whenever the preimage of the source map applied to this vertex is the empty set. And likewise, it is called a source if it does not receive any edges, which means whenever the preimage of a target map applied to this vertex is the empty set. So no edges end at this vertex. Okay, and these are very, very important concepts in it's not terminology, in our convention for graph algebras, because unfortunately there are two competing conventions for graph algebras. In our convention, the way we associate operators, generators to edges, sinks are of utmost importance. But if you do the opposite convention, then sources are of utmost importance. And of course, you can see that sources and sinks are interchangeable when you go to the opposite graph. So when you change the direction of all edges, then these two concepts are swapped. Sinks become sources and sources become sinks. So in our convention of graph algebras, these are sinks, which are absolutely pivotal. Yeah, because the consequent relations, as you might remember from the first introductory lectures, are not symmetric with respect to endpoints of edges and starting points of edges. Okay, now that we know what a source is and a sink, I can write the following cute proposition. If E is a graph with finitely many edges, and no loops, well, no loops, okay, maybe with finitely many edges without loops, and with precisely one sink, then this graph is connected. And for starters, maybe I'll convince you that you need these assumptions. It's not a proposition you can generalize. Alex, do you agree?
Yeah, sure. You mean the sink?
No, I mean, this proposition that I just wrote down, you cannot remove these assumptions. So first, if you have loops, well, this is a graph which has no sinks and no sources, right? Because every vertex both receives and emits, and it's definitely disconnected. So you must discard loops. Also, I can draw an infinite path marching from infinity to infinity, and then I can just add one edge. So you see, this is a graph which has precisely one sink, but it's not connected. Why? Because by putting into infinity into the game, I managed to put a disconnected component without introducing another sink. Okay? So I really need these assumptions. No loops and finitely many edges. And of course, when you have finitely many edges and only one sink, you'll immediately get that you have finitely many vertices. But yes?
So what is the issue if we have loops that we wouldn't
well,
call
look,
connected?
This is a disconnected graph and there are no sinks. So like if
there's no sinks?
Oh, yeah, sorry. Of course, I can just add an edge. Sorry, you are right, yes. Or I can simply add a point, a vertex. A vertex is both a source and a sink, right? This is a disconnected graph. I have exactly one sink, and the graph is disconnected. It has finitely many edges and exactly one sink, but it is disconnected, right? This has no loops, but has infinitely many edges and exactly one thing, and is disconnected.
So this is not only for the undirected graph, it's any graph.
No. All our graphs are directed.
Okay.
Yep. This is a default option. When you don't say anything, you mean directed. Because this is what this course is about directed graphs. And because we use it all the time, at a certain moment you skip, right? Like you don't say all the time the Republic of Poland, you say Poland, right? Okay. So now let's prove it. I like this proof. It's kind of obvious, very intuitive. So denote the sync by V0. I have unique sync, and with the help of English article, I can say V, and thus indicate its uniqueness. Denote the sync in E by V0. Okay, if it is the only vertex, in E, we are done. I think I erased the definition, but remember that connectedness was defined by saying that if I have a pair of distinct vertices, then blah, blah, blah. So if I don't have a pair of distinct vertices, the implication is satisfied. So it is a connected graph, okay? And of course, you wouldn't expect anything else. If I have only one vertex, absolutely every edge must begin and end at this vertex. So it is connected, okay? So I can now assume that I have another vertex, okay? So if there is a V1, which is not equal to V0, then I claim then there is a path, the usual path, directed path. Then there is a path from, of course, V1 to V0. And that's the crux of the whole argument, okay? Why? Well, indeed, as V0 is the unique edge, the unique sink, it means V1 is not a sink. It means that it must emit an edge. Call it E1. And now we sort of proceed by induction. If the end of E1 is not V0, then again, it's not a sink, so it must emit another edge, and so on and so on and so forth. And because we have finitely many edges at a certain moment, and we have no loops, so we cannot sort of go back with an edge, we must arrive at V0, okay? So let me write it down. So now consider any path emitted from V1. Maybe I'll write it explicitly. Any finite path, I mean. So Pn equals E1 up to En. Any directed path, Pn emitted from V1. For instance, the path P1, which is just equal to E1. Okay. Now, if the end of this path is not V0, then we have a longer path. Say Pn plus 1, which consists of E1 up to En, followed by some edge En plus 1, emitted from the end of Pn, which is the end of En. And if this end is not V0, it's not a sink. So it must emit something that's called the N plus 1. Okay? So hence, if no path from V1 terminates at V0, we have paths of arbitrary length. Which is impossible because we have only finitely many edges and no loops. Remember at the beginning, this theorem proved by my daughter, there was an argument. So in lecture notes, I refer to formula 1.1. Doesn't make sense to do it on the blackboard. We had this argument that if we have no loops and finitely many edges, then at a certain moment, if you want to extend the length of your path on and on and on, you must repeat an edge. And if you repeat an edge, you have a loop. So there's no, if you have finitely many edges and you want to have an arbitrarily long path, then at a certain moment, obviously you have to repeat edges, but then you would have loops. Yep. So this is basically, if you take these two things together, but we have finitely many edges and no loops, then you cannot have paths of arbitrary length, okay? Right. Obviously, if you have a loop, you can have paths of arbitrary length, but we will also prove the theorem going the other way around. And the crux of this argument was exactly as I put it, that if I would have a situation that no edges repeat themselves, but at a certain moment I run out of edges, so it cannot be of arbitrary length. And if I repeat any edge, then I must have a loop, so that's excluded. Okay, so which is impossible. Because we have finitely many edges and no loops. Okay. So therefore, as claimed, there is a path from V1 to V0. And now it's obvious how I end it, right? If I have a pair of distinct vertices and one of them is V0, the unique sink, well, I have a directed path. A directed path is in particular an undirected path. So we are done. But if I take two distinct vertices such that none of them is V0, then obviously I go with one path to V0, with another path to V0. They are joined at V0, and then they give me an undirected path that joins these two vertices, okay? So that's it, I just have to write it down. So now take any pair of distinct vertices. How do you note it? W1, W2. If one of them is V0, we are done. If none of them is V0, we take a path. Now let me not mess up the notation. Okay, a path Q1 which consists of some edges F1 to Fk from W1 to V0, okay? And a path Q2 from G1 to GL. Yeah, we have edges labeled from G1 to GL, and it's a path from W2 to V0. And combine these two paths into this time an undirected finite path. Well, Q1, Q2, which is a finite sequence F1 to Fk, followed by GL minus 1 up to G1. Okay, so here is my W1. I have a path to V0. And here's my W2. And I have a path to V0. And by putting these two directed paths together, we get an undirected path joining W1 and W2, so we are done. The graph is connected. Okay? It's just a cute little fact, but it is important. When you do graph algebras, you know, looking at things is always important. And we have a nice corollary, because at this moment you should say, well, are really things so much preferred over sources? What if I replace the word thing by the word source? Will it hold? Well, yes, of course. But let me now cheat a little bit and just change this proposition to corollary. I understand that there are no questions. I mean, these are all baby proofs, but I find them cute. So if E is a graph with finite linear main edges without loops and with exactly one source, then E is connected. Okay, now let me erase this proof and write the proof of a corollary. It rests on two facts. For starters, precisely because we use undirected paths to define connectedness, it's obvious that any graph is connected if and only if its opposite graph is connected. So let's first write this down. So for any graph E, the opposite graph E op is connected if and only if E itself is connected. That's obvious, right? It doesn't need an argument. Okay, and next, what do we note is that we know the following. A graph E has finitely many edges. No loops. And exactly one source. If and only if the opposite graph has finitely many edges. No loops. And exactly one sink. Right, the statement is obvious because when you just change the direction of edges, you don't change the amount of the edges you've got in a graph. Secondly, a loop is a loop regardless of its orientation. So any loop which is a loop in E is a loop in E op and vice versa. And of course, by the very definition of the sink and the source, by reversing the direction of edges, you swap these two concepts, okay? And now we are done with the proof because let's take a graph E without loops, with finitely many edges and with exactly one source. But it means that the opposite graph has finitely many edges, no loops, and exactly one source, one sink. So this means that the graph E op is connected. But this also means by this equivalence we started with that the graph is connected. So this ends the proof. Okay. So we have our proposition in two flavors, one with sinks and one with sources. Perfect symmetry. Okay, and I think this is as much as I wanted to say about connected graphs. Now we can go to hereditary subsets. No questions, I presume. You don't have a question, but I have a question. So let me write it down. And quite possibly there is an answer, but I'm not aware of it. So if you know it, please let me know. This is just my obsession with the maximal amount of paths, but now I phrase it slightly differently. So what is the maximal number of all finite paths, so any length in a graph with n edges no loops. I hesitated because I was thinking about vertices which are not in the image of the sort of the target map. But this is taken care of by saying that it's only one source and one sink. Okay, so no loops and exactly one source or exactly one sink. Sure.
Is this graph fixed or any kind of?
You know, any. The only thing which is fixed is the number of edges.
Okay.
So this is what we spent much of the previous lectures on. We fixed a graph with n edges, and we fixed a number k bigger than 1 and less than n. And we asked what is the maximum number of paths of length k. So this is a question in the same spirit, but now I don't want to maximize a given number of paths of a given fixed length. I want to maximize all of them. So this is a different question. Yeah, because each time it will be a different graph with n edges, which maximizes the amount of paths of length k. When you vary your k, you get a different graph maximizing the number of paths of length k. But I am asking what is the graph, right? Or a graph with certain properties that maximizes this amount of all paths. Yeah? And all I'm asking is that it is, you know, connected. And so it can be anything, you know, you can have something like a star, incoming or outgoing. You can have two vertices with all edges going from one to another. So all this kind of stuff is allowed. And, or it can have any kind of a tree with one root. Any kind of a tree with one root is also fine. Yeah. So this is what we are playing with. Mind you, we just limit the number of edges. And because we have only one thing and one source, we immediately limit the number of vertices. I mean, it must be finite, but it's not, you can have as many as n+1 many of them, okay?
Piotr,
yes?
So, I mean, like, just like before, when you defined undirected path, I mean, like, you know that you also could encounter, you would also take into consideration these situations that you just draw on the blackboard. Like the left-hand side would be like a path of length 4. No, of infinite length even.
Yes, so what's your point?
So I mean, like the way that you were thinking of like making it something like this, like, right, like flipping, for example, like a path and then like stopping like this and continuing like this.
I still don't get your point. I don't know.
I'm not sure how to explain it, but I mean, like, so you would, the left-hand diagram that you draw.
Yeah, this one.
Yes. What is the maximum number of an undirected finite path?
But well, of course, you can ask many different questions, but you see, I have a reason for asking this question, because if you would do a path algebra of this graph, that's the dimension of this path algebra.
Yeah.
So this is, if you want, a question of what is the maximal dimension of a path algebra on n generators, of an indecomposable, or if you want simple path algebra on n generators. This is a perfectly well-posed algebraic question.
There would be the number of directed paths.
Exactly. That's why I'm interested in directed paths, including vertices, but not undirected paths.
But I mean, like the definition before that you gave, I mean, I think like someone sitting also inside here also mentioned that you would also encounter something strange happening, like not like a really like an undirected path, what one would like view as an undirected path, but rather something like in what you draw on the left-hand side. Like the longest path that you would encounter here, the longest undirected path.
Yeah, would be 2, and the longest.
No, it would be infinite.
Yes,
it would be infinite. Because I mean, like because you say that only like, for example, you start with the one edge, you take another edge.
No. I mean, for this graph, you still have only finitely many undirected paths. This is obvious.
You have infinitely many.
Why?
Like if you run through your definition, like source equals tail, or source equals head, or source equals source. If you run all this, like if you run through the definition, I mean, you gave the formal definition.
Yeah, but I don't agree with your conclusion. I mean, how come you can get an infinite wherever you start your path?
Yes, you start with this one.
Yes.
You go one edge.
Yes.
Now you choose another edge.
Okay, this one.
Okay, and then you choose. Then the next edge, you could just simply choose another one because the source or the tail, no, the head of the next edge would agree with the.
I'm sorry, you're right. Sorry, I take it back. Sorry, Alex, you're absolutely right. Yeah, thank you. Yes, you're absolutely right. Because now I can come back, you see.
Yeah.
This is so strongly in my mind that I work with directed paths that there is a mental block. Sorry, I take it back. You're absolutely right. Thank you for correcting me. Yes, of course. Of course, because if you get into any of these endpoints, you can always come back. And this go.
You just need to match the head or the tail with the other one.
Yeah, you're right. You're right. But this makes the question about undirected paths uninteresting.
Yeah, you could just say, I mean, like the notion of an undirected path doesn't really have any use except like showing that like two vertices are connected.
Yeah, but this is exactly what I was saying.
But I mean, like the notion, the concept of an undirected path itself, like the path itself, I'm not sure this has really some use.
But this is exactly what I was saying. The only use it has is for defining connectedness.
Yes, so in this case, the notion of a path itself, an undirected path, has no use except for
directed path. So what's your point?
No, like I'm just saying, like the undirected path is, you could just say the equivalence relation.
So what?
It's not so important.
I understand what you're saying, but I don't understand what's your point. I mean, what are you trying to convince me of? You're saying a bunch of things which are obviously true. And so what? How does it relate to what I'm saying?
So just you have to be careful when you like define undirected paths.
Yeah, but I am careful. It's directed paths. I mean, and I made your point precisely by saying that I need undirected paths only to define connectedness. And this is why when I say path, I mean directed path, because I always use directed path, except for this one particular case when I define connectedness.
Yes,
so I fully agree with you, and I said it.
No, I don't mean for this question now. I mean for the stuff that we did before on undirected path. Just a hint, like when you define undirected path in the like what we did until now about connectedness. Not the question now, just the previous, like when you define, like just for the notes, like if you write some notes or something like this, that just that you bear in mind, like I mean, like that when you say undirected path, like what could happen?
Yeah, I mean, so here you made an interesting point that indeed, when you handle undirected paths, if you basically what you can say is that absolutely any graph which has at least one edge has the space of all undirected paths infinite, because the moment I have any edge, I can go back and forth all the time. So this is a very, very nice remark. I appreciate it, and thank you for correcting me here. But the rest, I honestly don't understand what you're driving at.
No, it was just a hint for what you wrote before. Like,
Okay, so but you see, let's focus on this question. Let's not get unhinged too much. This question is motivated by algebra, because this is a question about the dimension of a simple, if you want, one block indecomposable path algebra, which has, say, n generators in some sense. It can be presented with n generators. I mean, more when you add edges, but okay. Roughly speaking, what I'm telling you is not precise, but roughly speaking, it's a question about the dimension of a single block path algebra with n generators. What is its maximal dimension? Okay, that you can get for what graph? And this question gets more complicated when you go into graph sister algebras, because one of the things that you immediately know is that every graph sister algebra of a graph with finitely many paths is finite dimensional, and any finite dimensional sister algebra is just a finite direct sum of full matrix algebras. But because we are handling connected graphs, it means that this is just a matrix algebra. Okay, so in this setting, if I take graph sister algebra or Leavitt path algebra, it's one of the same thing here because we are finite dimensional, right? All that it is just a matrix algebra. Okay. However, here the thing is that you have to construct the extended graph. You have to have a push out of a graph E with its opposite graph over the subgraph of vertices alone and no edges. And when you take this extended graph, then you write down Kunstkrieger relations and so on and so forth. So the basis is no longer the set of all finite paths. There's a beautiful basis theorem in this book on Leavitt path algebras that is in the literature for the course, Abrams and so on. And this is more complicated. It's still given by paths, but these are special paths, not all paths. You have to make many exclusions. And yeah, you have a basis theorem, but it's quite sophisticated, and it's a variation of what you've got for path algebras. And here the count becomes difficult because you must include certain elements from your set to make sure that it's a basis, that the guys are linearly independent, because you have these Kunstkrieger relations. So when I'm in path algebras, well, one thing which is simple, I know that the number I'm asking about is the dimension, okay? But path algebras need not be matrix algebras. Okay, finite dimensional path algebra need not be a matrix algebra, it's wild. When I do the other way around, I say, okay, let's divide it by Kunstkrieger relations. Let's talk Leavitt path algebras or graph sister algebras, the same thing in finite dimension. Then I know that this must be a matrix algebra. No matter what, it must be a matrix algebra, full matrix algebra. But then I don't know how exactly this number relates to the dimension. Okay, so I find this question tantalizing. It's a kind of naive question everybody can ask. But to be honest, I don't know the answer to this question.
I think that the answer is the path, and the number of paths is n plus 2 choose 2.
Say it again, n?
N plus 2 choose 2 is the answer. The maximum.
N plus 2 squared, you mean?
No, choose 2.
Ah, choose 2. Sorry.
Yeah, and the path realizes this number. Like
so this is the maximal number of such paths, you say, right?
Yeah. I think that I'm not sure because I don't have full proof, but I have almost full proof, I think. I have kind of proof.
Okay. Okay, so you can say it when ready. So maybe not now because I don't want to disrupt the lecture.
Yeah, maybe I can present.
But I would be happy to hear it during recitation class.
Okay.
Okay, great. Okay, cool. You see, when you don't have questions, I have questions. When I don't have answers, you have answers. So this is collaboration. Okay, enough about connectedness and such stuff with one things, one sources. Now we go to the absolutely fundamental and standard concept of hereditary subsets, okay? There is no book about graph algebras or Leavitt path algebras which wouldn't write at length about hereditary subsets and saturated subsets, because these are the sets that allow you to characterize ideals for morphisms of Leavitt path algebras or graph system algebras, okay? So what I'm doing here is just pure graph theory if you want, but all of this is done with the graph algebras in mind. Okay, definition. Let E be a graph. A subset H of the set of vertices is called hereditary whenever any edge starting at any vertex V in H ends at a W which is also in H. So any edge that starts in H must end in H, okay? So then we call such a subset of the set of vertices hereditary, okay? So I can, right, so first let me maybe just tell you the following. I will not write it down. I will just explain to you on a picture the following observation, that we can have an equivalent definition. And I think, in fact, in the literature, people once use this definition or the other one, but they're completely equivalent. You can think what happens if I change the word edge by the word finite path. And by the way, I forgot to mention that in this definition of connectedness, I defined it using a finite undirected path. But of course, if I would drop the word finite, nothing would change. Because like we had it before with loops and so on and so forth, I just wanted to avoid the mumbo jumbo of defining what is the beginning and the end of an undirected path. It's a lot of trivialities, difficult to write down. Of course, if you have any path, even infinite, joining two vertices, then of course there is a direct undirected subpath that joins these two, undirected finite subpath that joins these two vertices. So I lose nothing by putting finite, and I avoid the problems of defining the beginning and the end of an infinite undirected path. Okay, so what if we exchange edge for a finite path? Well, are these definitions equivalent? So of course, you can say that one is stronger, because if any finite path has this property, then of course any edge has this property, because an edge is a finite path. It's a path of length 1. But how about the other way around? Okay, so assume that we have, this is our set E0, this is our subset H, okay? And assume that we have a path that starts in H and ends in W outside of H. Well, the point is that no matter how hard you try, at a certain moment, you must have an edge which crosses the boundary, right? At a certain moment, you will have to have an edge which starts in H and goes outside of H. Because if you don't have it, then you cannot have such a path. Then you are done, because if there is a path which goes from H outside of H, then there is also always an edge which goes from H outside of H. So the definitions are equivalent, okay? So instead of writing a lot of English words, I prefer a picture here. In the lecture notes where it's difficult to make a picture, you have English words, but on the blackboard, let me just have a picture, okay? So you can interchange these two phrases and you have an equivalent definition. Okay, so that's the first observation. Now, let me give you some absolutely elementary examples. So first, something completely obvious, that in any graph E, both the empty set and E0 are always hereditary. Right, this is obvious. If you choose the empty set, then, well, there is no vertex or which you can start an edge. If you take E0, there is no vertex beyond E0, okay, at which you can end your edge. And in this graph, that's the Toeplitz graph. For those of you who know Toeplitz algebra, this is the graph of Toeplitz algebra. If I look at this graph, I label my vertices as V and W. V has a loop and W is a sink. Then here, when I look at W, this is hereditary. Obviously so, because it's a sink. So it does not emit an edge. In particular, does not emit edge, but does not end in W. But the one element set V is not. Well, because in addition to emitting a loop, it also emits an edge which is not a loop, so it doesn't end in V. So it's not hereditary, okay? And now there is this promised simple little fact about this definition of hereditary. Namely, you have a certain standard construction of a subgraph. If you give me a subset of a set of vertices, then I can define a subgraph in a natural way, and this is exactly what happens for graph algebras when you want to get morphisms. If you remove all vertices that are in the subsets, together with all edges that end at these vertices, then you get a nice subgraph. But you get a nice subgraph if and only if the set of removed vertices is hereditary. Okay? So in fact, there is a purely graph theoretical characterization of your subset H of a set of vertices being hereditary. So let me phrase it as a proposition. Okay, so let E, which I now will write down explicitly as the quadruple E0, E1, S, and T, be a graph and let H be a subset of E0. Now, let me define F0 simply as the difference set. So this is E0 less H. Okay, so I'm taking out these vertices. And let me define F1 as E1, but with all edges that end in H removed. So I take the preimage of the target map of the set H. Okay? So I defined for you the subset of vertices, another subset of vertices, another subset of edges. Okay? Given a subset H of edges, I defined for you two subsets, F0 and F1, a subset of vertices and a subset of edges. Okay, so then the formulas SF of E equal to S of E and TF of E equals to T of E for all E in F1. Define a subgraph F, which is F0, F1, SF, and TF, a subgraph of E, if and only if H is hereditary. Okay, so if you look at this example, so the one element set consisting of W is hereditary. So if I remove this vertex W, and if I remove the only edge which ends at W, I just get a circle graph. And it is a subgraph of a Teplitz graph. But if I do it the other way around, I take my V, which is not hereditary, and I remove V, and I remove all edges ending with V, which means that what do I get? I get V removed and the loop removed. So this is not the subgraph because I have an edge which has no beginning. Okay? Then by this construction, this edge from V to W remains, but there's no V any longer. So this is not a subgraph. It's just that you know what we are talking about. Okay, so let's prove this proposition. So note first that if you take an edge in F1, which you have defined here, so I'll not write it down again. Then TF of E, which is precisely T of E, by the very definition of F1, this is not in H, okay? Well, which means that this is in E0 less H, which is exactly F0. Okay? So this always holds. There is no property used. Okay? So you see, so the conclusion is that if we take this construction, this quadruple, then you can always restrict the target map to the subset F1, and it will take its values in F0 without any properties. Okay? So T, which goes from E1 to E0, always restricts to TF going from F1 to F0. Okay? Good. Assume now that H is hereditary. We will need it for the restriction of the source map. Okay. Then, well, you take any edge in E1 if S of E is in H. It follows that T of E is in H. This is just the property of being hereditary. And hence we obtain the following sequence of logical conclusions. So if you have that E is an element of F1, which, let me remind you, is equal to E1 less the preimage under T of H. But this is if and only if T of E does not belong to H, right? Because this means that E does not belong to the preimage under T of H, so it means that T of E does not belong to H. Sorry, I should have crossed it. Okay, and this implies, so if you look at this hereditary property, we have that SE in H implies that TE in H. So TE not in H implies that SE not in H. So this is by hereditary property. Right? Then we have SE not in H, but, sorry, not in H. But this is if and only if SE is in F0, which is defined precisely as E0 less H. Okay? So I can conclude that, that S restricts to SF. S, which is a map from E1 to E0, restricts to SF, which is a map from F1 to F0. So the whole point is to show that if I take an edge from F1 and I apply S, then I must end up in F0. And this is what we just proved. Okay, so then we are done, because if both the target and the source map restrict to the subset of edges, then we have a subgraph, if you remember the definition of a subgraph. So now let's do it the other way around. Okay, so vice versa. Assume that S restricts to SF. then well, we have T of E not in H. This is, of course, as before, by definition, the same as E being in F1. So I'm not writing anything new. But now here, we use the assumption of restriction. If E is in F1, then we get that S of E is in F0, okay? But of course, this is if and only if S of E is not in H. So what we have proved then is that if S of E is in H, it implies that T of E is in H, so H is hereditary. So H is hereditary. In other words, we basically can reverse this argument. It's very similar. Here, the key implication is use hereditary to prove that T not in H implies S of E not in H. And here we use the fact that by assuming that we have a restriction, we have this implication. If E is in F1, then S of E is in F0. Okay, this ends the proof. So have a full equivalence, right, in this construction of subgraphs by removing a subset of vertices and all edges which end at these vertices. You can obtain a subgraph in this way if and only if the set of vertices which we remove is hereditary. Okay? So, surely, always. Just use the mic. You have a mic, right?
Yeah. I mean, okay.
Because you see, we hear you, but others, there are 10 other people on Zoom.
Okay. That's why
and it's kind of funny that they hear silence and when I answer to silence. So.
Okay, of course. Yeah. Okay. So may I ask the union of two kinds of this hereditary subset are also hereditary?
This is a good question. What I'm going to study is whether the property of being hereditary is closed under extensions of graphs or restrictions of graphs. And there is a complicated question to it. But if this is not completely obvious. Alex, do you know it by chance, what the answer is?
I must suspect it would be yes, but I'm not sure.
Sorry, what do you say?
So the question is that if I have two hereditary subsets and I take their union, then is it hereditary? Well, I partially, you see, in particular H, right, is included in H union H prime. And so let me answer this question later on when I'll study exactly how these two properties behave with respect to extensions of graphs or restrictions of graphs. And as I say, the answer is complicated. And I do it simultaneously both for saturation property and hereditary property. And as I said, the answer is complicated because first, these two concepts behave differently. And secondly, if you consider extensions of that form, then some things hold, which do not hold for arbitrary extensions. So, but this is not directly answering your question. Because here what you fix your graph, but okay, let's maybe try to figure it out. Maybe this is just much simpler because I'm not changing my graph. I have two hereditary subsets. Yes, I think this is obviously again hereditary because you see, what does it mean for this guy to fail to be hereditary? It would mean that I must have a vertex in the union, wherever it is, that emits an edge outside of the union. But this means this edge must be in one of these two subsets. So it must be, we must have an edge in H or an H prime, which emits something outside of H union H primes, and in particular outside of H. So then this is not hereditary. So this means that, sorry, so this is a very good question, and the answer is obvious. Yes, the union of hereditary things is hereditary. Okay, the same. I mean, intersection of H and H1 is no. Yeah, you might be, yes, you're right, sorry, you're right. You're right, here a counter example is immediate because you might have a vertex which emits edges like this, okay? So then this vertex doesn't violate the hereditary property of H, does not violate the hereditary property of H prime, but this does violate the hereditary property of H intersection H prime, yes.
I'm asking you a question because I thought there could be some probably a topology on this.
Yeah. No, these are very good questions. These are very, very good questions, and I haven't thought of them before, yes. But we have obvious answers. Yes.
So what was the question again? Can you phrase the question again?
Is the union of heredity, you fix a graph, because I asked myself a slightly more difficult question, you know, like relative topology. Imagine that you have a topological space and then you restrict it. So the question is whether if something is, say, open, closed, compact in a topological space, is it open, closed, or compact in a topological subspace with induced topology? So I ask analogous questions for graphs. If I have a graph and I have a subset H in this graph, and it has the property of being hereditary or saturated, does this property prevail when I restrict or extend my graph? Or not? And the answer is complicated, and I'm going to show you. Yeah, but this was a more involved question because I'm changing the ambient graph, like changing the ambient topological space for topology. But here, this is just, you have a fixed topological space, you have a fixed graph, and you're asking, well, is the intersection or union of hereditary? And the answer is absolutely obvious. The union is, the intersection is not, okay? Because if I take, so imagine that, I don't know, my graph consists of 1, 2, 3, 4, 5 vertices, okay, and 2 edges. We can have more edges. We can say add a loop here, okay, whatever. And now, that's the whole graph. That's the whole graph. And now I take set H, which consists of these 1, 2, 3 vertices, okay? And is it, and this one, oh. Yes, I think you're right. Yeah, sorry, let's do it again. This is when you don't think it over in advance. So we agree about the union, right? So we question again the intersection. Let's do it more formally, because sometimes when you just look at the picture, it might be misleading. So I have H and H prime hereditary, and I take H intersect with H prime, okay? And let me argue by contradiction. So let me assume that I have a vertex V in here, and I have a vertex W outside of the set, okay? And that there is an edge such that S of E is equal to V, and T of E is equal to W. So this is exactly saying that this intersection is not hereditary. So now I want to argue that it violates the property of H or H prime being hereditary. So since V is in the intersection of H and H prime, in particular is in H. Okay. So I don't understand yet. I mean, the problem here is that if I take if I take a vertex outside of this intersection, it doesn't mean that it's outside of H or that it's outside of H prime. So I don't see how it violates them being hereditary. Maybe an example I gave is wrong, but I don't believe that the intersection of hereditary must be hereditary.
You can, so one way to think of hereditary is by just saying what you do is you decompose your space into two disjoint pieces. And hereditary simply means in either way of convention that there's only one direction of transmitting edges.
Yeah.
And then it becomes clear that the intersection may fail to possess this property.
May fail, right?
Yes.
Yeah, that's exactly what I was thinking. Because I don't see how to complete this argument. But let's.
If you draw the picture again, and then you just say, okay, you notice that there's like inside H and H prime, like they can go both ways, transmitting and like transmitting in both directions. Think of a membrane.
Okay, so I'm interested in a vertex here, V, in the intersection.
And now you just draw edges. You just draw two edges that both lie in one of the components, say, for example, or either way. Just it happens all in the union.
Okay, so I surely to violate it, and without violating H and H prime being hereditary, I must have an edge which starts in V but goes outside the intersection, right? It goes without saying.
And one goes back inside the intersection.
What?
And another edge that goes back inside the intersection.
So you mean like this?
Yes, from either way, like from the one complement or the other complement.
Okay.
And then you have this, you don't have this property anymore that this wouldn't be, the intersection wouldn't be hereditary because it has edges transmitting into and edges transmitting out of the intersection.
Yeah, you're fine. I mean, just this one edge violates the hereditary property.
Yeah, that's
what I'm trying to think is why both H and H prime remain hereditary.
So H and H prime are hereditary?
That's it, because anything, so assume that this is the whole graph, just these two things.
Yes.
Right? Then H prime is hereditary because the only edge that is emitted from H ends no, H is not hereditary because this violates it.
Yeah, then you just draw like one, like both edges like coming and going into one of the H's and H prime, like not H and H prime. You just draw one edge that goes and another edge that goes in the other direction.
Like this?
No, you fix one vertex in one of the H's in the complement.
No, but I'm having the following problem. It's obvious that if I am to violate the hereditary property of the intersection, I must go with an edge outside of the intersection. That's obvious. And there are three possibilities. I can go to H, I can go to H prime, and I can go completely outside, okay? If I go completely outside, then it's crystal clear.
Yes, so
I violate the hereditary property of both of them, actually. If I go to H, then I violate the hereditary property of H prime. If I go to H prime, I violate the hereditary property of H. So Jacek might be right.
Oh, yes, good point.
Yeah, I think it's just a proof that. Yeah. So you see, Alex, you see?
Yes, good point.
Yeah,
yes, good point.
Jacek was right. Yeah. Yeah. Okay. Okay, this is good.
So we have an empty side and we have a full side. And
sure.
We have intersection, we have a union, both of them are
Sure, but you see, remember that in the definition of topology, you must be allowed to take either arbitrary unions or arbitrary intersections, not just finite ones. So, but you're right. But if I have a finite graph, then the set of hereditary subsets would give me topology on the set of vertices, except that it's, this is not the topology we are after. I mean, you're right. It's a good point, right? When you said it's finite, then okay, only finite intersection and finite unions make sense because you have only finitely many subsets. But and you know, you have the property of being hereditary close with respect to intersection, close with respect to union. The empty set and the whole set are in there. So yes, you have hereditary topology in E0. That's quite all right. It's just I don't know what it is good for. Yeah, it's a good point. I don't know what it is good for. One of the things I want to explain later on in a week, hopefully, is that when we go to the second property, the saturation property, I mean, you have sets that are not saturated, but you can always saturate them. It's like adding limits of points in a topological space. So this is like the closure operation. And you can make it precise, I believe, using Alexandrov topology. So the topology that we need to give on the set of vertices is not the topology just suggested, although you're absolutely right. It's definitely a topology for a finite graph, or at least a graph with finitely many vertices. But the topology given by order, we say that one vertex is less or equal to another vertex if there is a path from the first vertex to the next vertex. So paths give me an order, a partial order in my set of vertices. So this is a poset, and every poset has natural Alexandrov topology. And I want to show you next time, I hope it's correct, is that the saturation property which I'm going to define today, time permitting, because, oh my God, I'm already beyond time. But this is very enjoyable. I really like it this way. I really like such discussions. Then this is really the closure in the Alexandrov topology, but I will definitely not do it today. So again, I'm stealing you 15 minutes from the exercise, the recitation class, but at least let me finish it somewhere. Where are we? I think we are just done with the hereditary property. So in addition to what, but I'm going to type it out. These remarks, I'm going to add it into the lecture notes because these are interesting remarks. So in addition to what we just managed to see about hereditary subsets, we realize that they are closed with respect to both the union and the intersection. And for the union, the argument was obvious. For intersection, we had to hesitate for a while. I had conflicting opinions, but at the end of the day, we wrote the proof, which was somehow obvious with this picture. And of course, I could finish it here formally, but I think we are all convinced. Okay, so now I'm wondering how to do it. Yes. So let me do a few more minutes and then we start recitation class again, 1/4 past. I'm notoriously stealing you 15 minutes, but which means that in a week I have to give you back half an hour. Oh my goodness. So next week my lecture is only 1 hour. But it was worth it. I found this discussion interesting. So thank you, Shao. Okay, but maybe at least you will take home another definition. There's still time for it. It's slightly more complicated concept, and it's one of the concepts which has no direct meaning in terms of graphs alone. It's absolutely vital when you study ideals in Leavitt path algebras or graph system algebras, but I cannot prove such a cute proposition for saturated subsets as I prove for hereditary subsets. They have no equivalent formulation in terms of subgraphs of graphs or stuff like this. Okay, you need to go to algebra to see why they're important. Okay. And this definition is maybe a bit more awkward I mean, at least for me, it took a while to memorize it, to somehow come to terms with it, internalize it. And it's as follows. Let E be a graph, as usual. A subset H of E0 is called saturated. Whenever the following condition is satisfied. There does not exist a vertex outside of H, we would have the following properties. First, it is a finite emitter, emitting at least one edge. So if I look at the set of all edges emitted at V, the set is finite and non-empty. Okay, so this is first condition, but it must be a finite emitter, which is not a sink. Okay, and moreover, I want all these edges from this set. So T of S inverse of V. I want all these edges to end in H. So contained, because it's a set. Okay. So somehow we define it by contradiction. We say when a set is not saturated. A set is not saturated if outside of it I can find a vertex which is not a sink, which is a finite emitter, and it emits all its edges into my set. So what we do not allow, this is an H, this is a V outside of H. We have 20 million edges mapping here, okay? Mind you, it becomes okay if there is at least one edge mapping outside. It's also okay when I have infinitely many edges mapping inside, like for the Podley sphere. But what is not allowed is that I have non-zero and finitely many edges all mapping from V outside of H into H. Then this is not saturated. And the saturation property means that I include all such vertices inside. That's the saturation. It's like adding, the closure of a set is throwing all limits points into a set. Yeah, I have a set which is not closed, so it means it has some limits points of sequences or nets, if you want, inside that space that are the limit points are outside of a set, and then when you add them, that's the closure operation. So here it's sort of the same thing. These V that break the saturation property for H are like limit points. To make your set saturated, you have to throw them in. And you have a property of the saturation, and I hope to prove in a week that this is exactly the closure in the Alexandrov topology I just explained, okay? And where? Oh, yes, thank you, of course. Of course, of course. Yes, thank you so much, of course. Yeah, I said it and I didn't write it. It's, but luckily in the lecture note it's correct. Yes, of course. This is a non-existent. So that's why, I mean, this property is not so immediately absorbed. You have to get used to it. At least I had to get used to it because it looks like many strange conditions. But I promise you, the moment you work with graph algebras, these are absolutely natural and they understand what's happening. Basically, what's happening is you see what we want. We always think of constructing a subgraph in such a way that the Leavitt path algebra or graph system algebra of a subgraph is obtained as a quotient from the other graph system algebra or Leavitt path algebra. Okay, And you see, if you have such a situation, and if you remember the Kunz-Krieger relations, then basically by killing all vertices in H and all edges ending in H, you would have to kill all edges starting at V. But if you kill all edges starting at V, you also kill V. But you're not supposed to kill V. So you have this discrepancy between the construction of a subgraph and the Kunz-Krieger relation, okay? There's no Kunz-Krieger relation when you have infinitely many edges. I mean, it has a different form, not this finite sum. And if you have another edge, you are done, because if you kill all these edges, there's still one edge here. So killing all these edges does not kill your vertex. But if all infinitely many map into H, and you kill all these edges because they map into H, and this is how we construct the subgraph, then you also kill V. But that's not what you want to do, because the set of all vertices that you kill is supposed to be in H. But this is a graph algebraic explanation, right? I cannot give it a meaning in terms of graphs. So this is weird when you just look at graphs, okay? And I hope to justify the Alexandrov topology in recitation class. You know. Okay, so let's resume a 2:15. So we have 11-minute break, and I'm sorry for extending it again. But at least we finished with a definition of saturation. And I stop recording.